What if the internet you're using right now is just a preview? Today, we're diving into the quantum internet, a network that isn't just going to be faster, but it's fundamentally different, built on the absolutely bizarre but incredibly powerful rules of quantum physics. Let's get into it. All right, so here's our roadmap. First, we'll look at the big promise. What can this new kind of internet actually do for us? Then, we'll get into the secret sauce, the qubit, and its seriously spooky connection, entanglement. After that, we'll see how scientists are actually building this thing. And finally, we'll face the single biggest challenge standing in the way. So, what is all the fuss about? Why are we pouring billions of dollars into this wild-sounding technology? Well, it all kicks off with one revolutionary, game-changing promise. Just think about that for a second. An internet where the very laws of physics make it secure. Imagine a network where just trying to eavesdrop on a message would instantly vaporize it. That's the core idea here. And believe me, an unhackable network, that's just the beginning. Yeah, beyond perfectly secure communication for things like banking and national security, a quantum internet could link up quantum computers all over the world, creating one massive distributed supercomputer. It could lead to sensors so precise they can detect gravitational waves or see what's happening inside a single living cell. And it could even create perfectly synchronized clocks across the entire planet. Okay, to understand how any of that is even remotely possible, we need to zoom in, way in, down to the quantum level and meet the absolute star of the show, the qubit. You see, our entire digital world, everything on this screen right now, it's all built on classical bits. They're just tiny little switches that are either off or on, a 0 or a 1. Simple. But a qubit is playing a completely different game. Thanks to a wild property called superposition, it can be a 0 and a 1 at the exact same time. And this isn't just some clever metaphor. Superposition is a real fundamental principle of quantum mechanics. It means a single qubit can hold way more information than a regular bit. It's not just an on-off switch, it's more like a dimmer dial with a whole spectrum of possibilities all at once. The best way to picture it is like a spinning coin, right? While it's up in the air, spinning, it's not really heads and it's not really tails. It's in a state of both possibilities at once. It's only when you measure it, when the coin finally lands, that it collapses into one single answer, heads or tails. A qubit works exactly like that. So superposition is what gives a single qubit its power. But you can't build a network with just one, right? You need them to connect to each other. And that brings us to our next concept, entanglement. And I promise you, this is where things get truly weird. Entanglement is this bizarre, almost telepathic connection between two qubits. Once you entangle them, they act like a single system, no matter how far apart they are. So if you measure one and find out it's a 0, you instantly know, that its partner is a 1, even if that partner is on the other side of the galaxy. It's no wonder Einstein called it spooky action at a distance. This idea of a shared destiny, that's the core resource of the quantum internet. It's not about sending information faster than light, let's be clear. It's about creating a perfect, secret, synchronized link between two places that you can then use to do amazing things. So this entanglement is everything. It's what makes things like quantum teleportation, transferring a quantum state from one place to another, possible. And because of a fundamental rule in physics called the no-cloning theorem, you literally cannot copy a quantum state without destroying it. So any eavesdropper is immediately found out. And that brings us to the most important point. The main job of a quantum internet isn't to send data like ours does. Its main job is to create and distribute entanglement. Okay, so we have the mind-bending physics. We have qubits and spooky action. But how in the world do you go from that theory on a whiteboard to actually building this thing in reality? Well, the researchers see it happening in stages, kind of like leveling up a video game. Stage 1, which is actually already being built in a few places, just uses trusted stations to pass secure keys back and forth. Stage 2 is the big jump. That's where you're distributing entanglement directly between users. And the final stage? That's the holy grail, a full-blown quantum internet that connects powerful quantum computers all around the world. Now, a massive problem is that these quantum signals are incredibly fragile. They fade out over very short distances. And you can't just amplify them like a Wi-Fi signal because looking at a quantum state destroys it. The solution is a totally genius device called a quantum repeater. It basically takes two separate, short-distance entangled pairs and stitches them together to make one long-distance one. And here's the magic trick. It does all of this without ever looking at the data it's handling. Whoa, okay, don't worry about memorizing what's on this slide. The only reason we're showing you this is to make one key point. Building the quantum internet isn't just a physics experiment anymore. It's a full-on structured engineering challenge with blueprints and protocols that look surprisingly similar to the ones that built the regular old internet we use every day. But all of this incredible work, all this brilliant science, it all runs headfirst into one enormous, fundamental problem. The quantum world is just ridiculously fragile. A quantum state is so delicate. I mean, the slightest little vibration, a tiny change in temperature, a stray magnetic field, anything at all from the outside world can make it collapse and lose its information. This process is called decoherence. Basically, this environmental noise is constantly creating errors, and fighting that noise is the central battle in all of quantum technology. To give you a sense of just how big this challenge is, for a quantum system to be truly useful, it can only have about one error for every trillion operations. Let me say that again, one error per trillion. Right now, our best hardware isn't even the same universe as that number. So how do we ever hope to close that gap? Well, the answer is an ingenious idea called quantum error correction, and its hero is something called the logical qubit. The idea is brilliant. Instead of relying on one fragile physical qubit, you encode the information of one perfect qubit across a whole team of flawed physical qubits. By constantly checking the team for errors and making corrections, the system can protect the important logical information from the noise that's hitting any one of the individual players. So even with that clever trick, there are still huge engineering problems left. We have to figure out how to translate quantum information from the qubits that store it, like a hard drive, to the ones that send it, like a fiber optic cable. We still need to figure out the best quantum GPS for routing entanglement across a big network. And of course, we need to design it all so it can scale from a handful of labs to a global system. But here's the amazing part. Despite all of these mind-boggling challenges, progress is happening faster than ever. The first real multi-city quantum networks are already coming online, linking labs and universities. The journey is definitely long, but the destination is getting clearer. And it all leaves us with this one tantalizing question. Once this is built, once we have this fundamentally new way of connecting our world, what new science, what new technologies, what new ideas will we discover that we can't even imagine today?